Right, let's start recording. Good morning. So we have heavy rain outside. That's crazy. But better than snow, no? Okay. So good morning, everyone. Today we'll go over lecture 12, which is more into optimizing sequence alignment. We call it partial sequence alignment, and we are going to know why we call it partial. Last time we covered backtracking, which a way where we go back from the original cell where we start filling the dynamic programming table in a goal of finding the location and the type of all those edit operation. And we rely on each of those arrows that we pre-computed as we move forward, calculating the entire table. And that was an example of the alignment. And this is the backtracking path or the alignment path. And we talk about cigar string, which is a way to represent very long number of operation, which those could be the edit operation that we extracted from the dynamic programming table. And we talk about how we can control the penalty score for matching, for match and mismatch gap, which includes the insertion and deletion. And this is was an example of how we can favor matches over gaps. And we can see the difference between this and the previous example, where we now have the entire alignment on the main diagonal. We don't have any detour or changing the path from one diagonal to another. Okay, so today we're going to cover a very interesting topic. It's a really hot topic. It's something you'll see a lot of research paper on the theory of the dynamic programming and on the math side of filling those tables. So the question is, how about the computational cost of sequence alignment? We give you some insights about the size of the dynamic programming table. As the sequence length grows, then the size of the table directly becoming very problematic. So let's see the first problem. So we said if we would like to compare Netherlands, the word Netherlands and Switzerland, we would like to calculate all prefixes of the other sequence and trying to compare it to this. And one way to represent it is to do all the shifted version of one sequence and compare it to the other. Why we do all those shifted versions is to cover whatever expected operation to have. It could be insertion, it could be deletion. And we say when we have inserted character, we're going to shift all the trailing character to the right. That's why we need all the right shifted versions. And when we have a deletion, all the trailing character will be shifted to the left because that vacancy in the middle of the sequence. That's why we need this second group of shifted versions. And it could make sense to have this kind of algorithm. However, it's really computationally expensive, and we replace it by something we call dynamic programming table, where we represent those shifted version only once instead of having two groups. So when we calculate any of those cells, we make the decision either we go with insertion or deletion, but not both of them. Here we have to calculate both of them. That's why it makes the cost really high. So it makes sense to use dynamic programming table because one of the properties of using the dynamic programming table is to save the computation and use it later on. So anything we save over here, we are going to use it next in the next cell. Anything we save here, we are going to use it next, 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 and so on. Why is that? Because all the prefixes are included in the next step. So the S is already included in the SW is already included in SWI, and so on. So instead of recalculating every time the S, you can see S is included in all of them. Why we waste the computation and keep recalculating that? We could just store it once and use it everywhere. So this is computationally expensive. This is still okay, better than this. However, it's still problematic. Now, the problem is coming from what we call data dependencies. The data dependencies normally limit parallelism. The parallelism is something that we aim for so that we can leverage whatever we have as a capability to accelerate algorithms. For example, in typical CPUs, computer processors, we have some ways to calculate things in parallel. For example, do you know anything we have as hardware that enable us to calculate things in parallel? We have GPUs, we have SIMD, single instruction, multiple data cores in the processor, right? We have multi-threading, we have multi-core, right? All of those enable us to really do things in parallel. But we could do it at the software level. For example, the for loop. Instead of doing 100 iterations one after another, we could enroll the for loop and then do things in parallel, do multiple iterations in the same time, divide it over multi-core and so on. And the things over here, do you remember this shape? So if you want to calculate this cell, those 3 cells should be really pre-computed. They should be ready before we move ahead and calculate that. Without having these 3 cells, it's hard to calculate that one. And this one limits us in the way we could calculate the table. For example, I cannot calculate the next row without calculating the first. Why? Because any given cell in this row requires these 2 cells to be pre-computed, right? And this one is in the same cell, in the same row, so it's fine. But the problem with these 2, this and this, right? To calculate this, I should have these 2 ready. And that's why it's required me to go row-wise. So finish the first row, then the second row, then the third row, and so on. So I cannot parallelize the table computation and start calculating something here without calculating that first. Or I could do it column-wise. So if I want to calculate something in here, I should have this and this ready. This is not a problem because it will be in the same row, so I will be calculating it anyway. But I need this and that to be pre-computed. And this and that are in different rows. So I need to calculate this entire column first, and then the second, and then the third, and so on. And this restricts me also to do it column-wise. If I don't want row-wise, I could do it column-wise. Or the other way to calculate it is what we call it anti-diagonal. So the anti-diagonal, this is diagonal shape, right? And this is anti-diagonal. So for example, if I want to calculate this one, I need to have this, this, this. So this one, this anti-diagonal is fine, but this one should be pre-computed in advance. When I'm here, this one, these 2 cells should be pre-computed so that I can calculate this, which is along this anti-diagonal, and so on. So now I have either row-wise, column-wise, or anti-diagonal. Now, to amplify the problem more, so think about 30,000 long sequence pairs. I need to calculate the similarity between them, either as edit distance or sequence alignment. And then I need to build a DP or dynamic programming table size of 900 megabyte. 900 megabyte. Why 900 megabyte? So first of all, is it realistic to have 30,000 as sequence length? Do you remember what sequencing technology provide that? Not nano. Not nanopore. So nanopore, yeah, this is a typical range. This is somewhere in midway, but this is the maximum for PacBio. Okay, PacBio providing me something between 10K all the way to 30K. Okay, for nanopore, somewhere, let's say between 20 all the way 4 million. Okay, so this is a typical range. This is normal to have it. And why we need 900 megabyte? So remember, when we need to build the table, we have one sequence over here, the other sequence over there. And we do initialization over here, initialization over there. And that's added the length or the width of this table by 1. And the height, or this is the height, this is the width, by 1. So that is to say we have here 30K, another 30K, and now we add 1 for initialization, which is not important, right? And that gives us 900, K and K will give you 1,000,000, right? And assuming each of those cells require a byte to store the value here, the number, then that is 900 megabytes. Now, it depends on the score, the penalty you use. If you use large numbers, then the byte might not be enough. Then that will be 2 bytes maybe, okay? So we have to be careful about that. 900 megabyte, it's really huge. Imagine that you need to load it entirely to your DRAM or the main memory, okay? But this is not the worst that you could have. If you are aiming for something larger, like 300 kilo, so that is going to give you 90 gigabyte. 90 gigabyte. So 300 again times 300. That's huge. Now, we didn't talk about 4 million. And that's still read sequence. We are not talking about genome to genome alignment. We are not building the dynamic programming tables between genomes. So you can think about yourself about this equation and how huge you could go. So this is m plus 1, and we talk about y plus 1 because the initialization, plus 1 in the other side. M is the reference sequence, which could be one of them, and the n is the query sequence, which could be the other sequence, right? And this times this give you the number of cells. And if each of those cells require a byte to store, that is what we got over here. Now the question, can we do something better? Can we reduce the requirement or the number of dynamic programming cells? So the first algorithm we are going to cover called banded dynamic programming calculation. Banded dynamic programming. Or normally in bioinformatics, we call the algorithm by the author name, the surname of the author. And this paper was published in 1985. We have Yukonen or Okinen, okay? So we call it Yukonen banded algorithm. However, the algorithm, the characteristic of it is the banded thing. So this is what makes it famous. All right, so the banded something could be dynamic programming, could be edit distance, could be sequence alignment, whatever you want. The same concept, banded concept, could be applied to anything that requires the dynamic programming table. It calculates only the cells that are within a parallelogram that has a width of 2b plus 1, 2b plus 1, where b is an integer number. So you can pick the integer number you like over here, and that will be the width of the parallelogram. So we are going to draw something over here. And we can use a color. We're going to draw really a parallelogram over here. And that's the only thing we are going to calculate, plus some margin over here and here. But at the end, it will be this shape, okay? Now, the number of diagonals, so this is the main diagonal, something from the corner to the corner, and this is the next, and so on. So we have all those diagonals. Now, how many of them need to be calculated? Only 2b plus 1, okay? Where b, again, is an integer number. And it has a range between 1, because it cannot be 0, to 0, then I'm calculating only the main diagonal. That's why I have 2b plus 1. 1, the plus 1 thing over here, is for the main diagonal, from here to here. So if I have b as 0, then I have only 1, and that will be the main diagonal. Main diagonal, what does it mean? When I have only the main diagonal in the dynamic programming table, what does it mean? I have a sequence here and a sequence there. anything over here will be the corresponding character. So I'm comparing character to character. That's it. What we call it, what we call this algorithm, if I have one sequence, another sequence, and I'm only comparing the corresponding character, one-to-one. That is the easiest, the simplest algorithm I could apply, which is Richard Hamming. Right? You remember Richard Hamming, the mathematician? So this is Hamming distance. Right? So if B is 0, then I'm doing Hamming distance. There is no point using dynamic programming. That's why B cannot be 0. Let's start from 1 to the length of the shortest sequence. And I'm sure you are smart enough to realize why the length of the shortest sequence, not the longest, the shortest. So think about dynamic programming table this way. So we have one large sequence, and we have another one very short. Could we have this case? Yes, but we didn't cover it. So in what we cover is Needleman, Wunsch, right? In Needleman Wunsch, the two sequences must be the exact same length, because I think what we call as global alignment. Okay, so end to end. This case we call it another algorithm, Smith-Waterman. And you can guess that this is a surname of one of the authors, and this is the surname of another author. Likewise in here. Okay. In this algorithm, yes, it's allowed to have one small sequence and another very large one. Okay. Have one short compared to a large one. In this case, if we have such thing, and we build that in programming table, then the main diagonal over here would equal to the length of which sequence? So for each character here, we have a column, right? For each character in this sequence, we have a column. And for each character in here, we will have a row. So now it depends on the diagonal that you are going to cover. If you are going to cover things in the middle, so you're going to choose this, probably you could detour in here, keep going in the same one. It really depends on the alignment. And then you arrive to here. Or in this algorithm, you cannot have this thing, right? Because you cannot do end-to-end in Smith-Waterman. In Needleman-Wunsch, you would do something like that, but it's not allowed to have difference in length. And then what you are going to do is only to cover the character in here. So you're going to have something like here and then end it over here. You're not going to have any of those characters. So this diagonal over here, which is not main, because not covering the two corners, right? This diagonal over here, which is this cell, this, and this, could be shifted anywhere. So you could have it in here. This is 4 cells. So you could have it in here, here, and here. That's fine. You could have it anywhere. It depends where the sequence appears in this sequence. So if it's aligned somewhere in the middle, then we expect the alignment to be somewhere in here, here, and here. We won't have this case. We won't have that case. Hopefully it's clear. Okay. In such situation, always the diagonal where we have the alignment is equal to the length of the shortest. Otherwise, we won't have characters, right? How we can align this to this with longer alignment. Even if we have a detour, even if the alignment is splitted, and let's cover it again. Even if the alignment is spread over multiple, this one, and then it detours to something else, like here. So it covers 2 diagonal. It still equals to the number of characters in here, okay? And this is how we represent insertion or deletion, for example. So that's why we have the range from 1 to the length of the shortest sequence. Is it clear? Okay. So it's very useful when the optimal alignment is guaranteed to be found if it has at most B edits. This is the most important point in this slide. It's really important. So banded dynamic programming calculation, it's very useful when the optimal alignment is guaranteed to be found if it has at most B edits. Let's see what does that mean. So now, let's forget about Smith-Waterman. Let's focus on Needleman-Wunsch, which is 2 sequences of the same length. All right? Now, what is optimal alignment? The optimal alignment is the backtracking path that we cover after calculating the entire thing. So think about, we calculate the entire dynamic programming table, and now we do backtracking. So we already figure out that there are some arrows over here, then detour, some arrows, 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 until we arrive at the end. That is optimal alignment. Now, do you remember this shape? That is the range where we are going to calculate the cells, and everything else will be forgotten. Okay? We're not going to calculate anything here, anything there. So if this path is not covered in this area, then gone. Then we are not going to calculate the optimal alignment, and we'll give you something else. So you might calculate some part of it, whatever here, but whenever you detour in here, you're going outside, and that's not going to be calculated. And you probably will calculate something else, something like this, or you'll continue here, which is not optimal. Okay? It will be second optimal. Now, that is the first part of the sentence. Now, what is the second part of it? Why at most B edits? So we said the main diagonal, calculate, raise this thing. We said the main diagonal is always the thing connect the 2 corners of the table. Okay. Now this is the main. The distance from here to here is B, and the distance from here to here is B also. Okay. So it's symmetrical shape. So we have a B diagonal here. If B2, for example, then we have this is the main diagonal. We calculate 2 diagonals next to it from the left and 2 next to it from the right. Okay. Now, if you focus really too much about it, you will see something, right? Like the alignment will start appearing in the main diagonal if no insertion, no deletion, even if there are substitution, even if there are exact match, always will have the alignment at the main diagonal, right? The moment we start having an insertion or deletion, start diverting from the main diagonal either to the right or to the left, right? So the alignment start appearing at the next diagonal here, detour from here, and then going to the corner, or the opposite direction. Detour from here, and then start appearing here, and then go to the corner. We saw this several times in many examples where the backtracking, after we calculate everything and start backtracking from here, we start seeing covering multiple diagonal. Maybe we have a slide for that. Yeah, this one, for example. So here, this is the main diagonal, right? Maybe you can use this. So this is the main diagonal. Now you can see we start calculating on the main diagonal. The moment we start having an insertion or deleted character, which is I, right? Assuming this as substitution, replacing the character, then we start moving from this main diagonal to the next diagonal. So this is the next diagonal. right? So now we cover how many diagonals? 2. So we move from one to the next, and then we move here. Now, if we don't have this diagonal covered in this shape, we're not going to calculate it, okay? So how many diagonals in this shape will be calculated will be dictated by the number of edits that we can detect, right? So now assume we have this, we have in here, something happened as insertion or deletion. Now, what if something again happened here as insertion or deletion? What will happen? We are going to revisit the next diagonal, which is this one. Okay, so we are going from here, right? Again, what if something happened here? We're going to visit the next diagonal, right? Keep moving. Now that, if all those edit operation of the same type, if they are all of the same type, if this is a deletion, keep deleting, you will keep moving in the same direction, always in this direction, okay? Delete more characters, and you will move to the next. Now, the moment you do opposite, if you are doing deletion and you start having insertion, you will move in the opposite direction, which is this way. Now, think about, we are not going to have those deleted character, right? We're still in here. So we have only one operation that dictates the movement from this diagonal to this. And now we start having something in here as opposite direction, maybe a different color. Now, the moment we have this different edit operation, what will happen? We will move in the opposite direction. Excellent. Which is this way. So we are going back to the main diagonal, which is this one. Okay. Now, what will happen if we have again another insertion? Excellent. We will open the new diagonal, which is in here, number 6, and then we are going to move in this direction. If we have another insertion over here, so we're going to move in here. Now, how many edit operation do we have here? Have 1, 2, 3, 4, right? How many diagonal do we cover? We have 1, 2, this one, it's still the same diagonal. Don't get confused with it. This is the main diagonal. So we have 1, 2, 3, 4, right? And we could cover 4 edit operations, right? But let's have this example. This is a bit more interesting. Again, same story, nothing changed. We have the main diagonal over here. Yeah, maybe a bit shifted to the 5. Let's keep going over 5s. Yeah, that's the main diagonal, right? Okay. Now let's have a deletion as usual. And then we are going to shift the calculation in here. Okay. But now let's have an insertion here, where we are going to shift the calculation to the main diagonal, right? So we're going to this direction. Now let's have a deletion over here. What will happen? We're going to move back in here. Let's have insertion again, where we are going to move in this direction. Now, if we have another deletion, we're going to move back to this diagonal. How many edit operation happening here? 1, 2, 3, 4, 5, but we use only 2 diagonals, right? So that's why in this slide, we say at most B edits in a sense that you could have more edit operation covering in the same over here, but still the number of diagonals that you want to calculate and guaranteed to be discovering any B edit operation is B diagonal in this way and other B diagonal in that way. Although you could do less than that. Although you could cover, we already cover here 5 edit operation with only 2 diagonals. So we don't need the B diagonals, assuming B, for example, is 5. However, since we don't know where are those edit operation, and to be in safe side, we always require, if you have, for example, 5 edit operation, then you need always 5 bands to the right side, 5 bands to the left side. Okay? And we see that example. So that is the meaning of the second half of this sentence. This is very important to decide what B size you are going to include. And this is important for your programming assignment. That's why I'm trying to emphasize it, because you are going to decide what B value you'll be using. All right? Do we have any question?
We only calculate the values that are inside that erosion?
Yes.
But earlier we said that like in order to calculate values you have to
Exactly. Yeah, excellent. That's why I said within some margin over here and some margin over there. So you'll see the shape is distorted toward the end and distorted over the beginning. So we'll see an example. So the parallelogram, you'll see it somewhere in the middle. In the beginning, it will not be that shape. It will be something else, maybe triangle this way. Okay, and over here, same thing. So it will be this way, because we are going to cover the last column as well. However, those are exception. Don't think about them. What's important is to think about the number of diagonal in the middle, because it's consistent. You'll see that, but that's an excellent question. So the last thing, it leads, the banded dynamic programming leads to large speed up and storage saving, and you will see that. Now your question. So can you tell me what B value we are using here? So where's the main diagonal? It's not the blue one. Because obviously you can see that we detour from one to another over here and from one to another. The main diagonal is in here. Okay, that's the main diagonal. Now, if you want to check the B value from here, it's a bit confusing, right? Because in here, we have how many cells calculated? 3 next to the main, because this is the main, right? This is the corner. So how many diagonals? From here, 3, but from here, 0. So it was hard to know from here. But if you go anywhere in the middle, this is a bit shifted. So let's continue on 5, 5, 4, 3, 3, 3, 2, and then in here. Okay, it's a bit shifted in here. Sometimes I'm not good in drawing. All right, so if you go anywhere in the middle, what you will see that we have always 3 and 3, 3 and 3, 3 and 3, right? And that is the shape that you were asking about. However, in here, it's just something else, which is you can think about it as whatever. That's the boundaries of the parallelogram. And there's something else. I don't know what we call this shape. Okay. So now the B value is equal to 3. We have 3 diagonal to the right side of the main diagonal. We have another 3 diagonal to the left side of the main diagonal. right? That's in total 2b plus 1. So it's always easier for you to look over the corner in here and see if this is the main diagonal, then those number of diagonal, because each one of them will lead to a diagonal in here. So we have 3 in here. That's the easiest way for you to look. But if you're ever confused about the 2b plus 1, because here there's no 2b plus 1, it should be somewhere in the middle. And you should look at it horizontally, not vertically. You shouldn't go this way, for example. You shouldn't go this way. Okay? You should always look at it horizontally to find the 2b plus 1. Hopefully this is clear. Let's take an example. Right. So in the previous example, we said, I'm using too many colors today. In the previous example, we said the 30K 1000, it's going to result in 900 megabytes, right? Now, if we are using a band size of 10, a B value of 10, what will be the banded requirements for the table size? Now, again, the boundaries of the table is 30K and 30K, right? However, we're not going to calculate everything. We will calculate only this shape. And we will see an example how we are going to calculate that. The size, we said, is 10. This is the main diagonal. So this is 10, and this is 10. So we'll have 2 times 10 plus 1. That is 21 diagonals, right? And the diagonal size will be equal to the minimum of any of those 2 sequences. Why minimum? We saw that example of Smith-Waterman. In Needleman-Wunsch doesn't matter because both of them same size, so there is no minimum. So at the end, it's just any one of them, so the diagonal will be equal to that length. Okay? So 21 times the 30K, that will give you that number, 630 kilobyte. Again, the byte, assuming each cell requires a byte to store the value in each of the cells. So the savings are huge. So you can think about 1,428x times less in size. That's something tremendous. All right, now let's see an example of how we calculate the banded alignment. Now this is exactly the same thing as what we have in edit distance. Nothing changed over here. Initializing is the same. The equation will be the same, and this shape will be as a reference for us. So I already initialized the table, okay? 0, 1, 2, 3, which is the index over here, 0, 1, 2, 3, and so on. So the indices of this table will be the initialization value. Now to calculate this is not a problem, right? You always can do that. What is the value over here? So the algorithm is simple. If the character is similar to the character, do this. Are they similar? Yes. So what we should do, just take the value in here, copy it over here. That will be 0. Right? Now, let's continue. In here, is the value same? No. So we should apply the second condition, which is 1 plus the minimum of these 3 values. What is the minimum over here? Is 0, and then 1 plus, that will be 1. Okay? Now let's continue. How far we should grow? The B value here is 3. So how far we should continue? Excellent. So what is the main diagonal? This cell, this cell, this. So maybe we can have it in different color. So that is now continue here. Yeah. That is the main diagonal. And then remember, horizontally, we need to calculate 3 cells in here. For example, this included. So it will be this way. And in the other side, we have 1, 2, 3. So this is the limit. Okay. So at any given cell, for example, here, the main diagonal, 1, 2, 3. We should calculate that, right? Now let's go here. How we calculate that? A and G are not similar. So let's take 1, the minimum of those, which is 2. Did we arrive in here? We still have 1 more. A and T, not similar. So we don't have a cell here. What should we do? So here, this is the main diagonal. We already calculate 3 cells to the right. So there is no cell over here. This is empty, right? What we should do? How we should apply this equation? To calculate this, we need this, this, this to find the minimum out of them. For this one, we consider as does not exist. So you just cancel the condition, which is the brown one over here, or the orange. So you can imagine that does not exist. Then we are going to take the minimum out of these 2, which is 2 plus 1, 3. Okay? As simple as that. Now we calculate here. Are they similar? No. So we take the minimum 0, 1. Now are they similar? No. We take the minimum, then 1. Are they similar? We take the minimum, 1, now 2. Are they similar? Yes. If they are similar, we just copy the value in here, 2. Did we arrive? Not yet. We have 1 more. T and G not similar. So we take the minimum out of only these 2. Okay? Which is 2 plus 1, 3. Right? G. Let's continue because this is important. Let's see what will happen here. G and A are not similar. Let's take the minimum, 2. G and C not similar. Minimum plus 1. G and G are similar. We just copy the value in here. G and T not similar. What we should do, take the minimum, which is 1 plus 1, 2. G and G are similar. So we just copy the value in here. Did we arrive? Again, if you ever forget what is this, go back to the main diagonal, count 1, 2, 3. So we should calculate here. So G and G are similar. Just copy the value in here, which is 3. Done. Okay? Now let's move in here. Again, if you are not sure if this boundary is including the cell or not, go back to the main diagonal, count 1, 2, 3. So we should stop here. So we should not calculate this one. Now we are here. Is T and A similar? No, we should take the minimum out of those. We ignored this one. The minimum is 2 plus 1, 3. And we continue moving forward. Now you'll see some differences at the boundaries here. Comparing to the full dynamic programming table, you will see some discrepancies around the boundaries here and there. Why? Because in here, we might make some wrong calculation because we don't have the value here. So what if this is the minimum value? What if this is 0? And then 0 plus 1 is 1. So this one should be 1, right? So that's what makes some differences with the full dynamic programming calculation. Around the boundaries here will be something different. Okay? However, it's guaranteed to find the optimal alignment and the correct number over here, regardless whatever happening over here. Although the difference might propagate to something else. However, the optimal alignment always will start from here, and those values normally are not affected by anything over here. So those might propagate from here around those values. Might this affect even the cells over here because everything will rely on that. However, anything related to the optimal alignment relies only on the things in the beginning. And those normally are not affected unless we cannot detect at most B edits. That's why this is very important sentence in the previous slide. Okay. And hopefully you can imagine different type of alignments that require really B bands to the right, B bands to the left. Now, everything else is still the exact same way, so we may not continue building it, okay? But you could do it in your own. And the answer will be here. Yeah, we almost got everything correct. Any difference? No? Yeah, this one is, I made it myself just for the examples. It's not here. So you can continue doing the exact same thing, right? And that will be the alignment, which is exactly the same as the alignment in the full dynamic programming table. So the results are not different. So we still have 3 differences as number of edit or edit distance, and that is the backtracking path. You can see highlighted in red, okay? And now we save the computation. We only calculate this area. We don't calculate anything here, anything there. So that's a huge saving. And you will feel the difference once you implement it yourself. Try to implement full dynamic programming table, and then implement this, and you'll see it yourself. Okay? Any question? Yeah, excellent. You need to take care of this or that. Okay? How you'll do it, normally you should call this main diagonal something, and then you check the indices of those cells to the right and left. If you are exceeding a 3 count or whatever the B value, you can call it B here. If you exceed the B values, just don't calculate that. And you know, if you are in the left direction, then you'll never have this. If you are in the right direction, you will never have the things in the above. Okay? So you could have 2 equations, one with the thing in the down without the above, which will be used for the right side, and another equation will be used without this, but with this and that. Okay? All right. Now, sorry, we need to use the whiteboard. So I might not get the slider down. I hope it's visible. Can you see the text? Good? Okay. Yeah, if we get this down, we'll have some trouble to get it back. But yeah, let's continue. Now, what if the alignment path goes outside the band parallelogram? What will happen? We talk about we require at most B edits that we could detect. That's why we need B bands to the right and B bands to the left. What if the alignment path resides outside? So we move over the main diagonal, and then we detour to the next diagonal. We got another deletion. We now outside, another deletion, we are outside. What if we got this shape? So the banded alignment would fail, would not detect such thing, and the number you will get here will be wrong. That's why we have another algorithm called adaptive banded dynamic programming. Adaptive banded dynamic programming. And this is something recent in 2018 compared to the previous one, the banded. And the algorithm called Suzuki-Kasahara, which are the 2 surnames of the authors. Now, the algorithm says it calculates only the cells that are very close in value to the minimum score in each row. Now, instead of dictating number of cells to be calculated to the right and the left, so here, for example, we have 4 cells, but here we have 3 cells. And that is based on the minimum score in any row. So the middle point for us, instead of being in the main diagonal, now it can be shifted to the right or to the left, depending on what? The minimum score in each row. So if this is the minimum, then we are going to have right and left. If this is the minimum, then we are going to have left and right as well. Okay? So the center point for us can be shifted to the right and left. And that is helping us to cover things that residing outside the shape. Okay. Now, if the optimal alignment is this way, then the entire thing will be covered this way. And those are the cells will be calculated. It's no longer a regular shape. Okay. It determines the minimum score, M. So M is the things in the middle. Whenever we have a minimum score, we call it M. And this is very important. Remember M. Okay. As progresses and then calculates a cell that has a score of at most M plus A. So now we have another thing called A. What is A? A is similar to B value. Do you remember the B diagonal in the banded algorithm? Now this is similar to that. And that's what you need to determine before you start calculating. Okay? Now this is the thing you need before you start calculating. But this one, you don't have any control over it. You don't know it, and you don't need to define it. So this one is the minimum value in any row, which will come as you grow. Okay? And now, instead of having 2b plus 1 as the boundary for the parallelogram shape, now what you will have as M plus A. In any row, you cannot extend your calculation beyond M plus A value. So in any cell, if the value itself exceeds M plus A value, then you stop calculating and you move to the other direction. Okay? So remember, any cell should not exceed the value M plus A. That's very important. And we'll see an example. It's useful by adapting the number of cells to be built based on the optimal alignment path instead of a fixed number, as we saw in the banded alignment. Leads to larger speed up and storage saving compared to banded. This is a bit subjective because sometimes it really depends on how many cells you calculate. Sometimes it might be more than the banded, okay? More than the banded. So it won't give you saving. Sometimes less, sometimes more, but most of the time more. Okay, we will see that. Now, always things will be much more clear when we have an example. This is a very similar example to the banded. So we have the same sequences over here. We already initialized the first column, first row. Here, remember, we are calculating at a distance, not sequence alignment. So that's why we have this equation. And now we have the A value as 2. Okay, the A value as 2. Now we have the main diagonal, which is again here. That is our main diagonal. Now M plus 2. So we are not going to calculate 2 diagonals to the left and 2 diagonals to the right as we did in the banded. What we are going to do, M plus 2 is the maximum value for any given cell. Okay? Now what is M? Is the minimum in each row. The minimum in each row. What is the minimum here so far is 1. Okay? So M plus 2 is the maximum for us. Now this one is calculated. 1 plus 2 is 3. Okay, so we are good. 1 is included. How about this? Let's calculate it. Is A similar to A? Yes. What we should do, based on the equation, if this equal to this, then use the value in here, which is the blue one. So we are going just to use the 0 in here. Okay, this will be 0. Is 0 still within the range? Yes. Move on. Now, what is the minimum in here? 0. So no longer 1. So we switch M from 1 to 0. Now 0 plus 2, now our limit going down. Now it's 2. Okay? Because 0 plus 2 is 2. Is 0 within the range? Yes. Continue. A and C, are they similar? No. Then we cannot apply this condition. We move to else. What is else saying? 1 plus the minimum of these 3 cells. So in here, we have these 3 cells, 0, 1, 2. What is the minimum? 0. Then plus 1 is 1. Is 1 within the range? Yes. Then continue. Is the minimum still 0? Yes, because the minimum of this row is 0. Then this is still valid. Now in here, A and G, are they similar? No. Then take the minimum out of these 3 plus 1. 1 plus 1 is 2. Is 2 within the range? Yes. Then continue. What is the minimum? Is 0. Then this is good. A and T. Remember, we don't restrict ourselves for how many steps you can go far. You can go as much you want. As long as you are within the limit, then everything is good. Okay? Now, A and T, are they similar? No. Let's take the minimum. Now, in here, when we initialize, what is the minimum? 0, and then 0 plus 2 is 2. 2 is the maximum. So the moment we arrive in here, we stop. Now, why we calculate this in the beginning? In the first place, why we calculate it? Because we don't know if it's exceeding a limit or not until we calculate it, right? So that's why we calculate it. Although it's outside the range, which is 0 in here, plus 2, 2. So this is exceeding, but we don't know that in advance, right? So that's why we calculate it, although it's outside. That's why I told you most of the time we calculate more cells than the banded alignment, because we have to exceed the limit to know that this is the limit, okay? Now, in here, when we calculate the minimum, we don't have this cell, so we have only those 2. What is the minimum? 2 plus 1, because we are now in the second condition over here, because A is not similar to T. So 2 plus 1 is 3. Is 3 exceeding this? Yes, so stop. Now you don't do anything. Now you move to the next row. What is the minimum? Still 0, so everything is good. We're still using this number. Now in here, what is the minimum? 2 plus 2 is 4. So our minimum value now is 4. This M plus A is adjustable based on each row. So remember, M is the minimum number in each row. So for each row, there is different minimum value, okay? Now, is T equal to A? No, they are different. So what we are going to use, have the minimum out of these 3, which is 0 plus 1 is 1. Now, what is the minimum? Is 1. 1 plus 2 is 3, so we change the limit into 3, okay? Now, is T and C matches? No, so we should find the minimum out of these plus 1. 1 is still the minimum, so this value is good, and it's within the limit, so we continue. Now, T and G, are they similar? No. So what we should do, find the minimum out of these 3, which is 1 plus 1, 2. Is 2 minimum? No. So this value is good. Is it within the limit? Yes. So continue calculating. T and T, are they similar? Yes. So we just copy the value in here, and that will be 2. So same story, within the limit, and it's not minimum, so this value is still updated. Now we go T and G. Are they similar? No. So find the minimum over here. We didn't calculate that because it's exceeding the previous limit. So we just take the minimum out of these 2 values, which is 2 plus 1, 3. Now, is 3 exceeding? Yes. Is it a minimum? No. So we stop at this moment. Yeah, 3 is the limit. Oh, excellent, excellent. So it's still within the limit. Excellent, good point. So 3 is still within the limit, so we continue. We don't stop, okay? Until it exceeds the limit, okay? So now T and G, are they similar? No. So what we do, this is the only minimum we have, plus 1, then 4, okay? Excellent. Now, this is the limit, so we stop at this moment. We move to the next row. We have already 3 as initialized value. And then, now remember, we don't have anything in here. So we could go in 4, calculating in here, right? Because there is nothing over here, okay? But the moment you start calculating in here, you will see something very important that will tell you where to grow in here, okay? Let's see. Now, this is fine. 3, let's calculate it. This is the minimum. So 3 plus 2 is 5. So now our limit is 5. Okay. Now, G and A similar? No. What is the minimum? 1. Then this is 2. 2 now is the minimum, plus 2, this is 4. Are we within the limit? Yes. G and C, not similar. Then 1 plus 1, 2. Still the minimum value, so this is good. And within the limit, so we continue. G and G are similar, so we just copy the value in here. This is 1. Now 1 is our new minimum, so we update it. The M now is 1 plus 2, so this is 3. Are we within the limit? Yes. Are everything to the left side within the limit? Yes. So everything should be within the limit. Okay. G and T, not similar. So 1 plus 1 is 2. Is it minimum? No. Is it within the limit? Yes. G and G, similar. So we just copy the value here. Not minimum, within the limit. Continue. G and G are similar. Just copy the value in here. 3, within the limit, yes. Is it minimum? No. So G and C are not same. So continue. 4 and 3, what is the minimum? 3 plus 1 is 4. Is 4 minimum? No. So we're still using this limit. Is it within the limit? No. Now we exceed the limit. So we just stop here. Okay. Now we move to the next row. Now the things that you would observe over here compared to the banded, right? So this is the main diagonal. How many cells we calculate in here? Calculate 4. Okay. So we calculate 4. In here we also calculate 4, but in here we calculate 3. That's why we don't have a regular shape around the optimal alignment. In banded, we always have B diagonal to the right, B diagonal to the left. Okay? But in here, it's not regular. All right, now we move to the next row. Now we could assume this is 4. So this will be our limit, 4. Now T and A, are they similar? Oh, yeah, sorry. Excellent. Yeah. So now this is not valid. So we have the limit 6 now, because 4 is M plus 2 is 6. Now T and A, not similar, so take the minimum, 2 plus 1, 3. Is 3 minimum? Yes. So replace now the limit by 5. Now we have to go back. Is the thing we calculate in here within the limit? Yes. Okay, so continue. If it's not the limit, either you erase it because you accidentally start from here. You should start from somewhere else. Or you can keep it, but it will increase the number of edits. And I'm going to tell you a trick how you always guarantee to not calculate things extra in here. Okay? But let's wait until we complete this entire thing. Now, T and C, not similar. What we should do, just have the minimum plus 1, 3. Is it minimum? Yeah, same value, so we don't change. Is it within the limit? Yes, so continue. T and G, not same, so minimum 1. Now 2, is 2 minimum? Yes. Replace the limit by 4. This is good, 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 good. Okay. T and T are similar, so we just have this value, copy it in here. Is it minimum? Yes. Now 1 plus 2 is 3. This one exceeding the limit. Okay, let's have it, because we don't know if we are exceeding the limit until we have it. Okay, so we cannot erase it. Now T and G are not same. Minimum is 1. Now this is 2. So this limit is good. And we continue calculating. T and G, not the same. Minimum is 2 plus 1, 3. Okay. T and C, not the same. The minimum is 3 plus 1, 4. 4, exceeding the limit, we stop here. Okay. Now, next row, where we should calculate. Should we continue from here? Let's see that. Assuming we will calculate from here, but we will see that this is wrong. Now, G and A, are they similar? Now, first, our limit is 7. So this value is 5, which is the index copied from here. Now, G is 5. G and A are not the same. 3 is minimum, plus 1, 4. 4 is now minimum, plus 2, 6. So replace this with 6. Okay. I know this is very heavy lecture, so please pay attention to it. Now G and C, not the same. So 3 is the minimum. And now this is becoming 4. 4 plus 2, 6. So it's still within the limit. And everything is good. And this is the minimum. Yeah. Now G and G are same. So we just copy the value from here. Is 3 minimum? Yes, it's the minimum over here. So we update M with 3. And now this becomes 5. Now, G and T are not the same, so we take the minimum, which is 1, plus 1 is 2. 2 now is a new minimum in the row, so M is 2, plus 2 is 4. Now, this becomes quickly within the limit, but now it starts exceeding the limit, right? And we will see as we move here, start things coming here negligible. So the G now and G are similar, so we copy the value from here is 1. Now 1 is our minimum, right? Plus 2 is 3, so we update the limit to 3. Now this is far exceeding the limit, okay? So it was wrong to calculate this cell in advance. And now the trick to calculate the adaptive bandit correctly is that the moment you calculate in here, it's always good to go this way. Okay, don't calculate in here. So if you calculate, assuming this is your limit, remove one cell from here and start from here. Now, if this is the last cell you calculated from the previous row, you should start from here. Don't calculate those two. Okay, that is the trick, how you calculate it efficiently. Now, if assuming this row, you started from here and everything is good and this is within the limit, then you should start from here. Okay, one cell after in the following row. And then move ahead. Of course, you might find this is exceeding the limit, but you already calculated, so you cannot erase it. It's already done. The computation is done. Yes? Excellent question. So for those, this one you already calculated, right? This one calculated, done. So this one, assume you don't calculate it. So you cannot go from here, because even if you go from here, you can check the value to the left and you'll see it's within the limit. So you'll calculate it. And assuming you didn't calculate this and this, you calculate this in advance. So now you will go from here. But when you check the previous cell, you will see it's already within the limit. So you continue expanding in the opposite direction, right? So even if you don't calculate those, right, and you start somewhere from here, you'll see it's within the limit. Within the limit means don't stop in this direction. So you have to check this one, and then you have to check this one. And it might require you to adjust the value because this one was relying on this. And if you update this later on, you need to go back and update this, right? So that's why it's good practice. You might want to spend some time over here in the beginning, and then after that, just do the trick, which is just skip one cell from here and start from here. And you'll see it's always correct, okay? But that's a good question. So now we continue from G and G. They are the same, so we just have the 2 value. 2 is not the minimum, so we are following this limit. Now G and C, not the same, so we take the minimum 2 plus 1, 3. Is 3 minimum? No. Is it within the limit? Yes, continue. G and A are not the same. Take the minimum out of these 2 values only, which is 3 plus 1, 4. 4 exceeding the limit, we stop here. Now, we said we want to calculate from here, okay? This one. The 5 was in here, but we deleted, right? Let's keep it. If you start from here, you'll see that this is exceeding the value. Now, we want to start from here, but we don't have anything in here calculated. So is G equal to C? No. So what we do, we take the minimum out of these. 4 and 4, minimum 4, plus 1, 5. 5 is our minimum now, plus 2. The limit is 7. Now, you see that this is still less than the minimum. So you might want to check this one. Is G and A equal? No. So take the minimum out of these 2. Even if you don't have this, you have only this. So 4 plus 1 is 5. Is it still within the limit? Yes. So continue. G and nothing. so nothing to compare, but you could initialize this with 6. 6 within the limit, yes, so you can keep it, okay? Now, do you want to update this one? Since we update this value, so is G and C equals? No, take the minimum out of these 3, 4, 5, so still the same value, it's correct. Is 5 minimum? Yes. Is this limit correct? Yes. Now move ahead. G and G are equals, so just copy this value 4. Is 4 minimum? Yes. So update this into 6. Are you all following, right? Okay, great. So now G and T are not same, so we take the minimum 2 plus 1, 3. Okay. This is 3 minimum, yes. Now this is becoming 5. Now you start seeing that those already exceeding, right? So that's why the trick still works fine with this value. Now G and G are the same, so just copy the value in here. 2. 2 is now our new minimum. So this is 4. 4 still within the limit, yes, so continue. G and G are the same, so copy the value 1. 1 is our minimum, so this is 3. And we're still within the limit, so continue. G and C are not the same, so take the minimum and plus 1, 2. 2 our minimum, no, so it's still good. Within the limit, yes, continue. G and A are not the same, so take the minimum out of these, plus 1, 3. 3 within the limit, yes, continue, it's not minimum. G and C are not the same, take the minimum, plus 1, 4. 4 exceeding the limit, stop here. How's that? So now we see that those 2 are not needed because we already exceed the limit over here, and even in here we exceed it. So even this one is not needed, but we have to calculate it to know the limit. Okay? So it's always safe to move in here, and you don't need to check the things in the back previously. Okay? Now, I assume everything now is clear, right? We don't need to continue, but I have the complete solution ready for you, so you can verify. You might see some differences. This one is wrong. 1, 2, 4. Yeah, we have some extra cells here. Yeah, I may. Oh, the phone is working. Okay, so I need to take note of that. If someone can take picture of the slide with the handwritten notes, so I can update the value on the cell itself, on the table. Yeah, please send it to my email. I'm going to update the slide for you. But this slide is for your reference, so you can use it, right? And they try to solve it completely until the end and see how it works, okay? Really, without practicing, it's really hard to know. Maybe I can show this will be clear for you. All right. Now, I think we won't have examples, so I could have the slider back now. So I'm going to ask you in the programming assignment to choose one of these algorithms to be implemented. And that's why I provide you really hands-on example, because there are a lot of details. So every algorithm, I always say that all algorithms looks nice when you read them, but once you start applying them, you'll see a lot of niches, a lot of things in the corners. Yes? Exactly. Excellent. That will not be calculated. Okay? And that will going to save a lot of computation. That's why we call the lecture for today as partial sequence alignment or optimizing sequence alignment. Yes. So in the assignment, now the last programming assignment was indexing, right? And seeding. So now you start applying some of those indexing algorithm to the sequences that you got from FASTQ and FASTA-file, right? So the next assignment, you are going to detect the mapping location. Do you remember where we said about sorting mapping location? You sort all the mapping location, and then if green followed by red followed by blue next to each other, then this is probably a good mapping location, right? Then you are going to copy the exact same sequence. You already have the read, which you compare to this very long sequence. So you copy the exact same amount of characters as the read, if this is 100. So you're going to start from the very first match in here all the way to 100 forward. Pick 100 character. Now you have 200. Apply the sequence alignment in here. So use it for this to build the entire matrix. So this one sequence will be here. The other sequence will be there. And then build the table, but don't build it entirely. Yeah. Oh, yeah, definitely. Whenever you change any of those T sequences, you need to rebuild the entire thing from scratch. And that will going to change all those values. It will change the limit for you and so on. So you're going to rebuild everything. Does that answer your question? Yeah, excellent. Whenever we have any change over here as single character or the entire sequence, we have to rebuild the entire thing. Okay. If we change only something in here, so everything before that will remain the same. Everything over here will remain the same. So only we have to change this part of the table. Okay. Now, that's why we call it adaptive. It's really adapting all the calculation based on the sequences. If we change the sequences, all those will adapt itself, going to recalculate. But the banded one is always fixed. This is the banded. You might miss it, right? This is the banded, is always fixed. Regardless, whatever we have sequences in here, the area to be calculated is always fixed. It's not going to be changed. So the number of cells compared to the main diagonal is always fixed. We always have 3 cells to the left, 3 cells to the right. And that's always fixed shape. Okay? That's what we call banded alignment. So this is the main diagonal. Okay? And then we have 3 cells to the right, 3 to the left. Anywhere, it will be 3 to the right, 3 to the left. This is the main. This number 1 is main. Number 2 is the main here. The red cells, those are the optimal alignment, the backtracking. Once we calculate everything, we go from here, where we are coming when we arrive here, from here. Where we are coming when we arrive here, from here, and so on. So that is the answer for the cigar string. Okay? But the main diagonal is the thing that links the corner to the corner, which is this. That is the main diagonal. Okay? All right? For the adaptive, we said it's not regular shape. It's not always fixed width from right and left. Whatever we have the optimal alignment, we move ourselves. We adjust ourselves to be around the alignment to cover the number of insertion and deletion. All right. So now let's see the next paper that aims at improving the storage requirement. Okay? This paper is a bit old, coming from author Hirschberg. So Hirschberg is the name of the algorithm. As I told you, anything in bioinformatics, normally they call it with the name of the surname of the author. Okay? So Hirschberg algorithm. And it was proposed somewhere very old, which is 1975. Okay? So even before Needleman-Wunsch. It's a very simple technique. Do you remember divide and conquer? We already explained it in the lecture. So divide and conquer is where you have a problem. You divide it into 2 subproblems. You bring the subproblem, you divide it, you solve it separately, and then merge the solution until you come up with the solution for the entire problem. Okay? So simply is this way. Now we will come over it, but let's explain it simply. It says split, or we didn't cover this, a divide and conquer algorithm to compute half alignments. Half alignments. What does it mean? Let's see. So split the large problem into a few subproblems, recursively solve each subproblem. So you keep jumping until you arrive to a very small or trivial problem, and then you solve the trivial, and then you merge your solution until you come up with the solution. Merge the resulting answer. So let's see. Assuming we're going to, yeah, I need to draw on the, I don't want to bring it up. Might be hard to bring it down again, but you can imagine it yourself. So think about this sequence and this sequence, want to do alignment between them. Again, this is not the same length, so probably we are going to use Smith-Waterman, but this is not covered in the lecture, so just forget about it. Now, if you want to use Hirschberg, what it says split each of them into halves. Okay, that's why we have half alignment. So we have two halves over here. This is one, and this is one. So this and this are the two halves of this one. So this sequence we split into two halves, and this one we split into two halves. This is not even number, so we split into 3 and 2. You could do the opposite as well. Okay. Now the problem becomes from this to aligning those two sequences and aligning those two sequences. Okay. Now again, do recursively, because it says here recursively solve each problem. So split this into two halves, here and here. Here we want to split it into two halves, but maybe they have a limit into the problem size. Split into 2 and 0. You could split into 1 and 1. And then in here, cannot split more, because it will be one character and 1, and then 1 cannot be aligned to anything, so you keep it as is. In here, you want to split it into two halves, so T and T, and A and A, okay? And you do the exact same thing to the right side of the tree. And then now the alignment becomes the leaves. So those leaves of the tree, this, and this, and this, 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 and this are the optimal alignment. Okay, so T and T, exact match, substitution, exact match, substitution and deletion. Sorry, match and deletion. C and C match, A deleted character. Here, also deletion, a deleted character. And it makes sense why we have 2 deletion and 1, because this one are not the same length. So it will align only somewhere around, we have to delete these 2 characters, so it starts aligning from here. The T to T, A to A, C to T substitution, and then G and G match, and then C and C exact match, and A is deleted character. Okay? Is this clear? Now this is an example. It will be something like that. So the dynamic programming table, you split it into half and half, and do alignment only to this region. Okay, and then the other half and the other half, and you do alignment only to this region. And you split that recursively. So this one, you also have, okay, maybe I need to do that. And then also in here, you need to calculate only here, 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 and in here. Okay, and also in here, you have to calculate here and here. You might ignore these 2, you might not. It depends on the overlap. Now, why it works, although the optimal alignment, now sorry, this figure is flipped. We always have the sequence in here and the sequence in there, but I copy it from the paper. Okay? But you can imagine it, right? You can guess. It doesn't matter. So now the problem with optimal alignment from the corner to corner, what if the optimal alignment passed through here? Something like this. What if we have the optimal alignment this shape? It's not necessarily the optimal alignment will cross in the center or the middle of the table, right? So what will happen? So that's why the division over here, it's over the entire column. It's not only in the center. In this example, the overlap in the center, yes, but the division over here is over the entire column, meaning it might, this one, cover more rows over here. Or this table might go smaller than here. And that will come up with the alignment itself. As long as you cover the entire column in both tables, then you are good. Then you can cover all cases. Okay? Now the alignment, if it's passing through here, it might be over here and then in here, but you will see that clearly and you can fix it as you move around that. So you can increase the overlap, you can have it somewhere in here. And then you can fix the center for that. And for that, we have more control over the split. Rather than having always a fix to the center, what you would do, having a 2-parameter for the width of the cell, assuming this is always square. So this is the width, which is equal also to here, and the overlap, which is O. So what is the overlap in here? That is the size that's going to dictate how many cells that you could overlap these two. And that is with this paper called GAST. So recently, we start seeing less papers with the same name as the author name, as the surname. Why is that? Because the same author might be producing multiple tools. And then it doesn't make sense that he called all of them with the same surname. Okay, but almost all the old tools with the surname of the author. Sometimes they combine the surname of all last name, but you can see most of the people, if you are collaborating with someone, you'll continue collaborating with them. And then the exact same authors will appear in multiple papers. Okay? Now, this is an example covering how you can change the width and the overlap. So the overlap here is 1, meaning that we are going to overlap with a single cell most of the time, or single column most of the time. And then the tile size is 4, which is the maximum 4 by 4. Every time we'll have 4 by 4. And here we cannot have 4 by 4 because we're exceeding the limit of the table. Okay? But this is how you are going to divide the implementation. So now in the Hirschberg, we don't have such 2 variables. So we divide always over the middle and we overlap by single column, right? If you remember what we have over here, because we'll have one table in here, another one over here. That's fixed. But coming with those improvement, slight improvement over Hirschberg, you could have the T size or the width and the overlap so that you can say, okay, I'm going to, assuming this is starting from here. Okay, so this is the first character. This is the second character, third, fourth, and so on. So you need to adjust the way we think about it. So we always start calculating from here. Okay, but for this representation from this paper, they start calculating from here. Okay, but exact same idea. So if you want to start from here, it will be count 4 characters. This 4, maybe. Let's delete everything. Another color. So we start 4 characters. 1, 2, 3, 4. So we stop here. That will be the first table. Now, how many overlap is 1? Meaning, should go from here. 1, 2, 3, 4. So go toward the end. This way, 1, 2, 3, 4. So stop here. That will be the second table, if you want to do it the way we explain in the lecture. So we start from first character in here. Now, the remaining 1 overlap over here. And then you could do it this way, or you could have more to increase the precision of the algorithm. Okay? So anything in the middle, you continue doing 1 overlap 4 by 4 table until you arrive at the end. At the end, you could make the decision by having the entire column if you want, or you could just fill the last cell over here with this entries over here. Okay? Any question? Now for this one, you'll see that this and this pretty much rely on the value that you pick. If you pick a small overlap, then you are going to miss the optimal alignment. You're not going to capture the optimal alignment along the path. Okay? Likewise with the width of the cell. If the width here is small and the alignment somewhere happening in here, you might miss it. You might not provide optimal alignment. Okay? So that's why you have to increase the width to make it really something in practice a good value. And normally they said a width of 500 or more, a good value, and overlap of 200 plus is good number for overlap. Okay. Of course, this depends on the sequence length. That's why sometimes if you go with longer sequences, like 4 million with nanopore, is ONT, you might find these values very small. You have to change them. Okay. But those two algorithms still heuristics. These two are heuristics. Heuristics meaning that most of the time they provide optimal, but sometimes they don't provide optimal results. Okay. Yeah, we don't have to cover this. We can cover it next lecture, maybe. But now we already cover one Hirschberg and adaptive and banded alignment. So now we have 3 options to implement the last programming assignment. Okay. So please don't forget to submit the review paper draft. The due date is already passed. But please make sure if you didn't do it, so submit it as soon as possible. The programming assignment deadline was supposed to be today, but I shifted to the next lecture. So you have 2 days more. I asked the TA to do it. Probably today you will see it somewhere. Okay, that's why I extend the deadline. All right. Do you have any question? Thank you so much. All right. See you next lecture.